A very good morning to you all. Once again, welcome back in today's learning. As we have already started with and dealing with the Macaulay's method. Earlier we have taken certain numericals on that, and every problem was a unique problem. Here also, today we are coming up with a new type of a problem. Here on your screen, you can see this beam which is subjected to a uniformly distributed load, and it is not throughout the length, it is at the span CD, having the magnitude 40 kilonewton per meter. The lengths are being mentioned to you. Here we are required to find out the position and magnitude of maximum deflection. The parameters like E and I are given in the problem. So what is the uniqueness of this problem is, UDL is imposed, but it is not throughout, it is partial placement of this particular UDL for the span of CD. So let us see how this particular problem is to be dealt with. So initially we know, this being a beam, we have to find out the reactions RA and RB, and we know how to find out those reactions by the conditions of equilibrium. So by considering the equilibrium of whole beam, we are going to work out the various values of the support reaction RA and RB, for which we need to apply the conditions of equilibrium one by one. So I apply first sigma Fy, I got equation number 1. After that, second condition, sigma m about point A is equal to 0. So I will be taking the moment of all the forces here, known as well as unknown, about point A. So I will be getting RB is equal to 60 kilonewton. And once you get a value of RB, put it in equation number 1, you will be getting a value of RA. So now the first job is finished for this problem, that is to find out the reactions RA and RB. Now I will be placing that particular reactions here on this beam. Now what we have to do is another unique procedure which is to be followed for this sort of a beam, where partial imposement of the UDL is there. So what we are going to see, just watch it carefully. So here again we are having the same beam. Is it okay? Now what we have to do with this, I have to add additional UDL here. As I am adding additional UDL between D and B, I have to subtract that same magnitude of UDL there. Let us see how that is to be done, that is addition of additional UDL between a span DB, where actually there is no any UDL. What I wanted to do is, I am going to complete this UDL from C to B. For completion of that UDL from C to B, already there is C to D UDL, I have to add UDL between D to B. So I will be adding, as I am adding means I am going to disturb the given problem. So I am adding something, so I have to subtract something of the same magnitude but in the opposite direction. Let us see how that is to be done. So here you can see I have added UDL in the downward direction, right? As I have added it, I have to subtract also. So ultimately the result of these two UDLs newly imposed will be 0 plus 40 kilonewton per meter downward and 40 kilonewton per meter upward is going to nullify the effect. So due to this addition of UDL for the span DB and subtraction of the same magnitude of UDL on DB is not going to disturb the originality of this problem. So what I did is, I added additional UDL acting in the downward direction, and I have to subtract the same UDL acting in the upward direction. So this is what is the new thing we have to do when we are having a beam which is imposed by the partial UDL. In between the UDL is been placed. Is it okay? Now this is kilonewton per meter. So I think you have got this particular idea what I did, I added as well as subtracted the magnitude of UDL for the span of dB. Now the problem is a same problem what we have seen earlier. Whatever procedure we have adopted till now, the same procedure is to be now adopted after adding and subtracting the UDL for the span of dB. So what we used to do, we used to take the sections between two intermediate or subsequent load or the forces. First force, second force starts from here. So here I have to take first section, second section will be between CD, and third section will be between D and B. Let us see how that moment equation is to be written now. So take the sections one by one, second section and third section. After taking the section, the important thing is to establish the bending moment equation for each and every section. So for this we can say, in general, the bending moment can be written as, if I take a moment about this, so 100 into x. For this span, 100 into x minus 40 into x minus 1 whole square by 2. So this is 40 into x minus 1 whole square by 2 is the bending moment of this UDL that I have added to the bending moment of RA. Now when I talk about this particular section, what we have to do, we have to take the moments of all the forces on the left hand side. So RA into x minus 40 into x minus 1 whole square by 2, and after getting this, what we have to do, we have to take the last moment, that is for this UDL. Actually this is not last, one more UDL moment is to be taken. So 40 into x minus 5 whole square by 2. All of you getting? So what I did is, I took various sections, and about that section I am going to take a moment. So here for this 100 into x, for this UDL for this second span 40 into x minus 1, this is x minus 1 whole square by 2, and this is valid for how much length? From x is equal to 1 to x is equal to 7, or rather we can say 8. What is another thing remaining? The UDL of this. Here I don't have to take a separate moment for this, because this has been carried out from C to B now. The UDL is been imposed or considered from C to B, to which I have added this. So this particular thing, for this UDL which is acting in the upward direction, that moment we have to take here. So it is coming plus. Why plus? Because UDL acting in the upward direction about this section, its moment will be always positive. All of you getting? So plus 40 into x minus 5 whole square by 2. So why this is 5? Can you see this? Up to this point to this point, how much it is? 5, and from this point to this point it is x. So remaining distance is how much? X minus 5. So plus 40 in the bracket x minus 5 whole square by 2. Sorry. So this is what is the generalized equation for the bending moment. Now we know, after establishing or getting the bending moment equation at various sections, what we shall be doing? We will be taking the governing equation, that is EI due to y by dx square is equal to, right hand side is the bending moment. So substitute that value of bending moment what we have already found out here. So here I will be substituting that value of bending moment, and after getting this, we know what is to be done in the further steps. We have to integrate it obviously. So after integrating, what we are going to get? EI dy by dx is equal to 100 x square by 2 plus c1 minus 40 into x minus 1 whole cube by 3 plus 40 into x minus 5 cube by 3. So this has been simplified as 20, this also by 20. So we have this particular new equation. Now after getting this, we have two options, either to find out C1 right now only, or afterwards also you can find out the C1 after integration. So here I am rewriting that equation once again. So I call it as equation number A. Once again I will integrate it. I will be getting a slope equation. EI into y is equal to what? 50x cubed by 3 plus C1x plus C2. This will be what? Minus 6.33 x minus 1 raised to 4 by 4 and x minus 6.33 x minus 5 raised to 4 by 4. So this is how we have established second equation. Now our job is to find out the value of C1 and C2 one by one. This is a simply supported beam, and in simply supported beam, what were the boundary condition utilized always? Here if I draw the elastic curve, so at x is equal to 0, y is equal to 0, and at x is equal to total length, that is 8, again y is equal to 0. So using these two boundary condition, I will be able to find out the value of C1 and C2. So at x is equal to 0, deflection at A is equal to 0, put it in that equation number B, you will be getting C2 is equal to 0. So simply we have to put the value of x in this equation. So here you can see I am conveniently neglecting these two terms. Why? Because if I put x is equal to 0 here, so 0 minus 1 will be answer what? Minus 1, and as I told you, minus answer is not tolerated in this Macaulay's method. Here also 0 minus 5 will give you minus 5, so that is also not to be taken into account. So what we can say is only here. Another logical reason for this is what? As I am talking about x is equal to 0, so that is related to the first span, that is AC, and for this AC first section is there, and for first section this is the only bending moment, and the integration of that bending moment is here only. So take only first part of that total integration, eliminating these two remaining terms. So I hope you have got why I am again and again taking only first term, because I am dealing with what? X is equal to 0. X is related to what? First span, AC span. Now if it is to be only span AC, and that section will be what? This particular section. So about this section, bending moment is only this much. So after doing the double integration, it comes out to be here. So only first term I am going to take, and while working out the problem, if something comes out to be negative out of this bracket, so that is to be neglected. So here x is equal to 0, so 0 minus 1 is equal to minus 1, so this is to be neglected. 0 minus 5 is equal to minus 5, so this is also to be neglected. So these are the two logics behind which, and utilizing these two logic, I am simply going to take this first term for the calculation of C1 and C2 for this condition. Is it okay? So now you can see after putting this value, I got C2 is equal to 0. Now if I take the second boundary condition, that is x is equal to 8, y is equal to what? 0. So in that case, can you imagine, if I am talking about x is equal to 8, means I have to take first section, second section as well as third section, means I have to take whole bending moment equation and their double integration. So while having that equation of B, for working out the value of C2, I will be considering C1, I have to consider the whole thing. So this is how we have to work out the value of C2. Now take the second boundary condition, put it in equation number B. So here as x is equal to 8, means I have to take the whole term in equation B. So use that thing and find out a value of this. So this comes out to be 8 minus 1, that is 7. 8 minus 5 is equal to 3. So both are positive. After simplifying this total thing, I will be getting a value of C1. So I got value of C1 and C2. Now what is to be done? We have to rewrite this equation number A and equation number B. So rewriting that by putting the value of C1 and C2. So already we have the value of C1 and C2, put it here. So I got equation number A, also I got equation number B. So these are the two generalized equation for this beam, and which can be utilized for what purpose? For any value of x anywhere on this beam. If I have to find out the slope and the deflection, take that value of x, put it here in equation number A and B, you will be getting the value of slope and deflection. Is that okay? So here what we are needed to find out? We are required to find out here the maximum deflection, and we know where the maximum deflection is going to come. Maximum deflection will come where the slope is equal to 0. Is that okay? So here if I draw a tangent to the maximum curvature, this is the point where there is what we can say slope is equal to 0. So here that deflection is occurring between span what? C and D. Is it okay? So I will take that equation number A. Up to what values we have to take, or how many things we have to take? C and D. So only up to second section. Is it okay? So I will be taking only first and second term, not the third term, because we are dealing with the span CD, where I have taken second section, and about second section this is the maximum terms existing into that particular equation. So here put the values. dy by dx is equal to 0 in this equation number A. So here this will be equal to 0. So what is remaining? These three terms are remaining. Is it okay? So if I simplify that, you will be getting again. So here I have neglected this term, this one. The reason I have told you, as we are dealing with CD, so only up to the second section I have to consider the moment and their integrations. And here another logical reason is what? 0 minus 5 will give you minus 5. So minus is not taken in the Macaulay's method. So here after simplifying, you are coming across a quadratic equation. Solve that quadratic equation. I am getting value of x is equal to 3.82 meter. Once I get a value of x is equal to 3.82 meter, what we have to do? We have to back substitute in the deflection equation, because maximum deflection is asked for this particular problem. So put this x is equal to 3.82 in equation number B, solve it, simplify it, you will be able to get a value of maximum deflection that came out to be equal to minus 16.33 millimeter. Why minus? Because it is in the downward direction. Deflection is occurring in which direction? Downward direction. So this is the maximum deflection of magnitude 16.33 millimeter. So this is the procedure we have to follow when we are dealing with a beam which is partially imposed on beam in which UDL is imposed partially between C and D. So what we did here, I have added UDL for the span remaining, dB is remaining, so I have added. As I have added, I have to subtract that also, and after having this, the usual procedure is to be followed, and that procedure we already know. Following the steps one by one, you will be able to get the required solution. In this problem, it was asked to find out maximum deflection. We already know maximum deflection is occurring between C and D. So these two terms are to be taken for the further analysis, and because of that, after having or applying that particular condition, that maximum deflection will be occurring where slope will be 0. So take the equation of slope, equate with 0. I will be coming across with this particular equation, simplify it, you are coming across a quadratic equation, solve that quadratic equation, get a value of x is equal to 3.82 meter, take the equation of deflection, put x is equal to 3.82 meter, and this is how we have to get the maximum deflection for this beam, and we got y max is equal to minus 16.33 millimeter downward.